Hello. Thanks for the intro. That's when I grew the beard too. I was like, I'm ready. All right, let's do it. So now it doesn't work. Huh? Okay, there we go. So just a quick intro. So what are we going to talk about today, right? I'm going to do a small introduction. Is Python slow? What is slow? Then the experiment that I did to try to benchmark these things. Then I have a tour of different approaches: 311, PyPy, Cython, MyPyC, bindings with Rust, Mojo, and then some closing thoughts. Cool. Are we all ready? Are we excited? Well, thank you. All right. But first things first, right? Let me just some few words about me. So my name is Murilo. If you haven't guessed by now, I am Brazilian. How many Brazilians do we have here? Oh, okay. Actually, less than I thought. I feel like it's my first time in Portugal, actually, and I feel like there's so many Brazilians here. I never seen so many Brazilians, and I lived in Brazil, so I was like, okay. But I live in Belgium now. I have a bachelor's in mechanical engineering at a university in the US, Purdue University Northwest. And then I did not like it. I switched gears and I went to artificial intelligence at a university in Belgium. I have some certifications as well, not super important. Some fun facts. My main language is Python, duh. But also I've been starting to get more interested in Rust, right? So I'm not a Rustation. Whoa, okay, I like the excitement. But yeah, so I started like playing a bit with it. Seems interesting. And the last thing is that I think that everyone should have a chicken at their house. Chickens are great. They eat your food. You give your eggs. Just a side note. That's the kind of guy I am. I'm also one of the organizers of the Python user group in Belgium. And my day job is a tech lead for the AI business unit at DataRoots. So we are a consultancy company around data and AI services. So just some quick things there. And this is where I touch most with Python, right? So Python is a language that I deal with on a daily basis. And I must say that in the beginning, I was a bit confused, right? I learned programming mainly when I was doing the master's here. And you hear about AI, machine learning, that you need a lot of data, need a lot of compute. But on the other hand, you hear that Python is slow, right? So that always like confused me. Now I know better, but maybe curiosity here. Who feels that Python is slow? Okay, few hands. Okay, some wiggle there. Okay. And who heard that Python is slow? Yeah, okay, everyone, yeah. Because that's pretty much what I heard all the time, right? Just trying to do your thing and it's just like, oh yeah, Python is slow. Okay, but how slow is it, right? So I look at some benchmarks. This one here, they went through this formula a lot of times. And Python actually comes here at the 4th from bottom up, right? So apparently it is slow. But I wanted to see how slow is it really, right? So I did a small experiment. So this is the good disclaimer that I'm not an expert in these things that I'm going to show now, but this is my curiosity that drove me to try these things, right? Another fair warning that all benchmarks are wrong. But what I mean here is that benchmark is going to test some things, right? But it's not going to test the whole language as a whole. It's kind of like SQL benchmarks. We were talking about polars. There's a famous benchmark on that. And then it's like, oh yeah, if you have 1 terabyte of data with 1 group by and 2 where clauses, then polars is the best. Otherwise, DuckDB is this, like it's a bit iffy, right? So this is just to get a feel. So take everything with a grain of salt. So 2 small experiments. One is the Fibonacci. And also the other one is calculating the number of triangles in a network, right? So the Fibonacci, if you're not familiar, basically the Fibonacci number is the sum of the 2 previous numbers. So there's recursion there, some repetition, and calculating the numbers of triangles in a network is literally like you have a network like here, and you're trying to see how many triangles you have, right? So there's a lot of iteration. Graph algorithms are not super easy to do. They don't scale that well, right? So I wanted to give it a try. So something that is not, this I saw in documentation on some of these frameworks that I'm going to show. This one I didn't. So I wanted to try something that is not the happy path, right? All the code is available. I'm going to share the code. This is my GitHub. It's going to be there. Excuse me. And this is kind of the project structure, right? So this is my terminal recording, okay? The reason why it's messed up is because I wrote the integration with the slides thing, and it's in JavaScript. So of course it didn't work well, right? But when I hit play, it's gonna hopefully resize and everything will be there. So how slow is Python, right? This is my baseline. This is 310. So I just activate the virtual environment and I'm just running here. So this script actually takes some arguments. So basically it's just like you have like I shown before, you have the Python, you have a Cython, which is a bit different, and you have the Rust one. So I'm just running the Fibonacci number with 40, right? Calculating the 40th Fibonacci number. And then this is the number and it takes 31 seconds. This is on my machine. The code is going to be available. So if you want to try later, just so you know. Okay. And then the triangles, same thing, activate the virtual environment. You see here, there's Python 3.10. You see here, there's Python 3.10, and it takes 133 seconds, okay? So this is just to get us started, all right? So maybe before we actually talk about all these things, right? Like, can we make Python, like the actual, just the Python faster? And yes, we can, right? Like, if you follow the Lucas Lenga or on Twitter or now X, right? There's some noise about no-GIL Python, right? So Meta, Facebook, I feel like all the tech companies are changing their names, huh? But anyways, they dedicated like some Python developers to work on the no-GIL Python, right? When I shared this with my colleagues, their first reaction was, well, does it matter actually? Everything that needs to be fast is already written in C, right? Which is a fair point, but what I think, well, so maybe the question here is like, do we really care? I would say yes. I think that some things are like, if your user needs to wait 1 second, maybe that's acceptable. But if you wait half a second, it's even better, right? So performance is not like a yes or no. It's like more of a spectrum, right? And I think no one would say, oh, no, this script is too fast. Oh, I hate it, you know? So I think if you can make it faster, why not, right? Let's give it a try. And the other thing is that there is a cost of writing these things in C and then binding it to Python, right? So there's a developer speed as well. This is also a trend that I've personally seen. I personally seen on Python, right? 3.11, it was known as the faster C Python with Mark Shannon and whatnot. And then you have the no-GIL Python, which is what is referred here on this tweet, which is tentatively on 3.13. Okay, so let's see how much faster is Python 3.11 for these two use cases. So again, I'm just activating the virtual environment. It's a different Python, it's Python 3.11, so it's a different environment, and I'm just running the same code here, right? 3.11, and you see that we go from 31 seconds to 19 seconds, so it's a bit better. If we look at the triangles though, it's not gonna be a very big improvement. So same thing, and it goes to 123 seconds. Maybe just a disclaimer, right? Like this, the idle time I cut off of the recording, so just so you know, so you don't have to wait so much. I'm not an expert. I know that there was a talk earlier today about C Python and whatnot, so maybe I should disclaim as well. I'm not an expert, but this is some things that I gather playing around with it. Why is Python 3.11 faster? How do they actually make things faster? At least one way, right? So just as an experiment again, activate the virtual environment for Python 3.11. I'm actually gonna just make this bigger so I can pause this on 12. And I'm using the disassembly module, the dis module, which also it was mentioned yesterday as well. I create a simple function, this foo function here, and then I'm looking at the bytecode instructions. And the thing to keep track here is this binary operation here, right? Now, if I actually run this function 100 times, and I actually look again at the bytecode instructions, you see here that this got specialized to the integer type. So basically, Python sees like, okay, you're running this a lot, so let's optimize this, right? This is important. This is performance critical, right? Now, if I have a different function that instead of actually multiplying numbers, it would actually just check if an element is inside iterable, right? So this is what I'm doing here. And now, if I do the same thing, so I check the instructions, you have the contains op, you have all these things here. And if I run 100 times, we actually don't see specialization on this instruction, right? And this is, again, just to go back to my previous point, that Python 3.11 is faster, but it depends a lot on what you're using it for, right? Like there's no silver bullet. It's not like going to be faster for everything. And that's why I believe that the triangles example, it wasn't as performant as the previous one. Everyone with me? Yeah, so one none. Okay, I'll take that. So what if instead of doing this at runtime, what if we can analyze the code before and optimize the code for that? And that's what PyPy does, right? PyPy is a just-in-time compiler. I think there are some very small exceptions, but it's almost a CPython replacement, right? So if you just change the interpreter to use PyPy, everything should work. And actually, I haven't seen a lot of issues. When I tried, everything was really smooth, right? It's written in RPython, which is a subset of Python. It's reduced Python, right? And it's written for interpreters. It's not really for your code. And it's a JIT compiler, meaning that right before the code compiles, it will look at your code, see where the for loops are, see where the performance critical code is, and will optimize for that, okay? So process that is much faster, and there's very little overhead. for me, my experience was really just installing PyPy and just running the same thing. You're going to see it later in a bit. The cons, though, this is not for packages. This is only applications. So you cannot compile ahead of time, right? Like if you have something and send it to someone, I cannot send a compiled thing. And that's because PyPy, it actually uses memory addresses of the objects that are there, right? It's very specialized after you have the process running. So if you want to use PyPy, it basically to send you the same code and you need to run PyPy with. It's probably not worth for short scripts. There's also a cost of doing this JIT compilation, right? So if you have something very short, it actually may even take longer. Of course, it lags a bit behind CPython, right? Because they're always catching up. And it doesn't play well with C extensions, right? So stuff like NumPy, and this is the reasoning from the documentation, right? That they use the CPy extension, which is slow, and then they try to have workarounds for this. Actually, also they mentioned that if you have something that is C and it's critical, you should first re-implement this in Python and then run it if you really want to go that route, right? So, but this is a big downside here as well. To illustrate the cons, I have this very short script here, right? So I'm just going 5 times, creating a random NumPy array, and then calculating the mean for that. And so it's a very short script. Oh, this is really small, no? Is this better? Can people see this? The back? Yeah. Okay. So again, just running here, create the virtual environment, then I run the thing in Python. You see it takes 0.48 seconds. And then if I use the PyPy version, it actually takes 0.53 seconds. So it's a small difference, but also it's a short script as well, right? But this is just to say that it's not always going to be faster. There are some caveats here and there. All right. So now let's look at actual experiment, right? So I activate again the PyPy environment. So now I'm using PyPy and not Python. And then I run the same thing. And you see that the library or the code that I'm using is actually the Python code. So it's the same thing that I ran before. But instead of 31 seconds, it only takes 5.9 seconds. So a big improvement. And for the triangles, you're going to see something similar, right? Activate the virtual environment from PyPy and run the same thing that I ran on Python 3.10 and 3.11. And you see that it took 5 seconds or almost 6 seconds, right? So big improvement. But like I said, if you're building a library or something that someone else is going to install, you cannot use PyPy. So if you want to do that, one way you can do this is to use something like Cython. Cython is not new. Anyone who heard of Cython here? Okay, and who worked with Cython, implemented things in Cython? I see a wiggle there. Okay, 1, 2, 3. Okay. I had heard about it a lot, and I was curious, and that's why I wanted to give it a try, right? And it's still, even though it's old, let's say, it's still under active development. They recently released the 3.0, and originally, well, maybe let me go see. The way I understand it is that basically from your Python code, you create a C extension that you can actually use in Python again. Right? I'll show again once we have the experiments as well. It's also a superset of Python. So you have everything that Python has, but then you have also these different keywords like the cdef or cimport, right? And one of the things that they've been trying to do is to be more Python compatible. If you have a Python project and you decide it's slow, you can still use Cython. You can just do it after the fact. You can augment these .py files with Cython types in a separate file as well. Once Cython also offers things for bypassing the guild. The idea is that once you're in that C level, the guild is not necessarily applicable anymore. So there are ways you can bypass the guild with Cython, but it has some small limitations. I think like tuple unpacking or something like that. That's also not supported. Just to illustrate this here. So this is the pure Python, let's say, if you want to use Cython as well. So you can just put this here as a type hint. And this is one of the things that they've been working towards. But you also have the Cython, right, which is not valid Python. And even the extension changes, but you have this double keyword, you have the cdef and whatnot. So they do offer these two things. Okay. The people that use Cython, how did I do? Okay. Well, no. Okay, good. Okay. Got a thumbs up. Mission accomplished. So I also want to see what's the impact of typing in Cython as well. So on the Fibonacci, and it's just because the code is shorter. These are the implementation with the Python implementation, right? The normal Python, and this is using the Cython type. So the only difference here is that I import Cython and I actually use the Cython.int instead of using this. And just to be clear, this would also run on Python, right? This is a metadata. This doesn't get, they don't care about this at runtime. Okay. So let's take a look. I'm gonna make this bigger as well. So I create the virtual environment, and Cython actually comes with the CLI tool, Cythonize here, right? So you can run this, and I'm targeting the Python implementation. So with the Python types, And then you see that once you actually do this, now you have this C files and this binary files here. Okay, so that's what Cython is doing. Now, if I run with the Fibonacci with the Python implementation, which is with this optimized Cython thing, it took 10 seconds. And now I can do this with the Cython types. So again, do the same thing. It's on the Cython directory now, so it's slightly different. The structure is a bit different, but in essence, it's the same thing, right? And now if I run that, I actually get like even almost like 2x improvement. So my take on this is that if you use Cython, the Cython types, you still get an additional improvement over what you would have with just Python type-ins. Okay. So for the triangles, same thing. Activate the virtual environment, use Cythonize. Now you don't have to specify they're using Python 3 because on the 3.0 now it's the default, right? And using the same data first with the Python types, you get to 133 to 131. And now if I do the same thing with Cython, I get to 127. So the improvement is again smaller, but there is a small improvement there. And I'm thinking that it's something similar to what we saw with Python 3.11. Okay. So my PyC. So who knows my PyC? Oh, okay. Just John, 2. Okay, yeah, imagine. And who knows MyPy? Okay. So MyPy is the static type checker, right? And MyPyC is something somewhat similar, right? I don't want to dive in too much because we have other stuff to cover as well. But basically, it targets many similar keys to Cython. The way it does it is somewhat similar, but the approach is different, right? So the idea is that with Python type-ins, you should be enough for you to derive these things that Cython wants you to do explicitly, right? So it's more modern, I guess, in a way. They even go as far as suggesting a workflow where you use Python interpreter when you're developing. And in CI/CD, you can actually build these extensions which are optimized, right? So let's look how we work in practice. You just, again, activate the normal virtual environment, and I just use the Python. So I'm just MyPying the Python thing. You get the .so files, the binary files here. And if I run this with, again, the Python normal type-ins, I go from 31 seconds, which was the baseline, 6 seconds was in Cython, to actually 1.68 seconds. So much faster, right? And the same thing for the, well, triangles, but I'll let you see. I don't want to spoil anything here. Yeah, so 117 seconds. All right, so we were talking now about using C, basically in Python and binding it, right? So let's just talk about binding. So like right now, the strategy with MyPyC and Cython is you write code in Python, it gets transpiled to C, and that's an extension for Python back, but you could just write it in C, right? Or Rust, actually. So when I say bindings, is everyone okay with that? Everyone knows what I'm talking about? I'm gonna assume no, because I also have this bullet point anyways. But the way I see this is kind of like integrating Python with other languages, right? Python, one of the reasons why I believe Python is so popular is because it plays really well with C and C++, right? And this is also what you see with the machine learning libraries, right? This is the thing that confused me back when I was learning Python. Things like TensorFlow, PyTorch, or actually NumPy are basically C++ with a layer of Python on top, right? And recently, we see more Rust stuff, right? Rust coming to Python. That's also how Rust started to catch my eye, right? Things like polars, the previous talk, which I didn't know was a previous talk, but a good segue, right? Or Pydantic v2, which was also now written in Rust. So it's Rust with a layer of Python on top, right? So the experiment that I did is actually with Rust, right? I'm also trying to learn Rust. I'm trying to find excuses to do it. The way that it works, as I understand it, that Python has this libpython. It exposes the libpython, which is a C extension, and Rust, not extension, sorry, the C core. And Rust actually has a FFI, a foreign function interface that plays really well with C. So what they do, they take this and they expose this in Rust as safe types. So whenever you can run Python in a Rust program, basically they start a Rust process and you can run it in Rust, or you can actually have something in Rust that exposes the application with the C API that Python expects, okay? All in all, you can run Rust on a Python interpreter. That's what you need to know. So, and I know yesterday there was a question on this as well. So first thing I'm going to do is activate the normal virtual environment. And then here I'm using maturing, which is a tool, a CLI tool from PyO3 to actually, well, if you run maturing develop, it will first build the Rust project and it would actually install in your current active Python interpreter. Okay, so that's what it's doing now. And you see here that it's installed. And then now if I run the script again using the Rust, now I'm actually using the Rust with the Python binding on top of it, okay? And again, I know this is very fast, that's why I'm pausing. And you see that we go from like 31 seconds to 2 seconds. But we can do even better, right? We can actually pass a flag, the release flag, which is what cargo, the pip of Rust kinda-ish. Well, I'm not gonna get into that, to actually optimize the code, right? And then same thing, installs in your current active Python, and we go from less than 1 second. So pretty good. And with the triangles, I'm gonna do the same thing here. So first go to the Rust project, use maturing to build and install. And also maybe the question yesterday was about PyProject.toml. I don't remember who asked it. Maturing also has a build format for PyProject.toml, that's what you will specify. And you see that after improving the performance of everything, we actually get to 3 seconds for the triangles. So a huge improvement there as well, right? And last but not least, Mojo. Oh yeah. Who heard of Mojo? Who played with Mojo? Oh, okay. Okay, cool. I'm curious afterwards to hear your thoughts on that. Mojo, it's a separate programming language. Okay, that's the way I see it right now. And before you boo me off stage because this is PyCon, it does intend, it's striving to become a superset of Python, right? So it's almost as if I'm talking about TypeScript in a JavaScript conference, which maybe you're not okay with that, but to be honest, I kind of did that already with Cython, right? So I'm just gonna go with it. But it is not a drop-in replacement for sure. Like it still has a lot of very rough edges. It's still a very early stages. It came from actually the story behind is that the Modular, the company that created Mojo, they have this AI engine. And they actually started building this language to create this AI engine, right? And then they said, okay, let's just kind of keep going until it becomes a superset of Python. It's statically typed. Python is not. So if I say x is equal to 1 and then x is equal to high, Python is okay with that. Mojo is not okay with that. And it's also compiled, which is also not the same thing with Python, right? Currently, because of all these things, it basically feels like a different language with a Pythonic syntax. It has a high and low level. So the high level is like the Python or the Python replacement, and the low level is the superset part. Okay, I'm going to give some examples in a second. It has some AI features because of its history. It's very early stages, so there are no comprehensions. I know this next talk is about comprehensions, not in Mojo, sorry. It doesn't have dictionaries actually, so it doesn't have a lot of things, but the way that they try to bypass this is that it integrates well with Python. So you can have like a Python code and you can actually bring it into Mojo. You can even add two things like a Mojo object and a Python object. It would translate it, right? And actually, as of yesterday, anyone can just download and use it, right? So you have to register modular everything, but you can just give it a try. So, for example, there's no class, but they do offer, oh, sorry, maybe some examples. If you're also interested in more on how Mojo code looks, we have this awesome Mojo, which has some snippets, and we have actually this Mojo libc, which is a project on this, right? And again, if you open this, I think you're going to agree with me that it doesn't feel like Python. It feels like a different language. It's like, oh yeah, that kind of looks like Python, that small part there. But anyways, I digress. Mojo doesn't have classes, but they have structs. So this is just a decorator that basically tells you that this can be passed through the registry, not the memory. I'm not exactly sure what it means. I just read it in the documentation, but it has some lower level stuff that you can play with, right? If you use the keyword struct, then you also need to type your stuff. And I know this is capital F. This is how Mojo works, actually. And this var thing, which I'll talk in the next slide. And then you also have your methods here. So you have the dunder things, but you also have this fn, which I'll get to now. This is an example of the Euclidean distance written in Python. So pure Python and Mojo optimized. This would also work in Python, by the way, in Mojo, I'm sorry. But this is the optimized version, right? So let's go through the differences. First thing is that you have the fn keyword instead of def. If you have the fn, you actually have to specify the types. So you have to in Mojo. And again, the types are slightly different. These are all built in. And you see the tensor. So this is the AI feature. Variables, you have to specify with either var or let. And the difference between them is that var is mutable, right? So here we're actually changing the value and let is not. So again, things that you tell Mojo so you can make optimizations. This, according to the blog post, right? This is from blog post. This optimizes 60 times faster than Python and 2 times faster than NumPy. For our case, basically we have the high level Mojo, which is just like Python. And then the only difference between the two is that I'm actually using the int type int that I have to, and the fn keyword actually. All right, so if you have Mojo, it comes with like this CLI tool as well. Oh. And then if I just run this here, first the high level API, I guess, it took 4 seconds. And then the low level, it took 0.36 seconds. And this is the fire emoji, which is a valid file extension for Mojo, just to say. Also, the baseline is a bit different because when I tried this, I tried in a dev container. It was a bit different, the setup. So I had to retime my baseline, but this is what it got. So the improvement is actually way more, relatively speaking, right? And for the triangles, I was actually not able to do it. So let me go through my list of excuses why I couldn't give you this information. And I'll just skip through the things. I tried different things. I tried to refactor. I tried to write the reading part in Python and just import it into Mojo. I tried to rewrite the CSV reading logic in Mojo, even if it's really dumb. And I had a lot of issues. And in the end, the current state is that they were like, oh, there's a C++ file. There's an assertion error. Please file a bug report. I was like, so I was like, okay, let's just keep going, right? If you have any suggestions as well, this is open source. Feel free to create an issue, pull request. The code is available as well. So this is kind of it. In the interest of time, I'm going to skip through this. These are just all the comparisons put together. And just some final thoughts, right? High level, we basically have either different interpreters or different languages interacting with Python. Always benchmark and test your things, right? Just because this is what I've seen, you're going to may have different experiences with it. So try to be pragmatic and methodical about this. My opinionated guide based on what I've seen, if I have to improve the performance, is first go to Python 3.11. If not, I'll go to PyPy. It was really just like a drop-in kind of thing. If it's an application, so if it's applicable, try MyPy in Cython. Actually, it's MyPyC or Cython. Do the bindings in Py03 or Mojo. Right. I was talking to a friend about this, and they were like, well, if you're going to do all this, why don't you just write in Rust then? Like instead of using Python. And I was like, it's a fair point, right? But I would say as well that there is a cost of writing things in Rust, right? It's not as fast, like if you want to write C, C++, then writing Rust, right? So we also have to take that into account. And in reality as well, like from the beginning question, right? How many people think that Python is slow? Not everyone thinks that, right? Like what is slow? Like what do you need, right? So that's also a valid thing to think about before you start trying to optimize everything. So the way I see is like you can write something in Python, profile it, see if it's slow, see what parts of the code is slow, and then just kind of optimize for that. And that's kind of how Python is set up as well, right? If you think of things like NumPy or TensorFlow, is basically the stuff that doesn't really need to be that optimized is in Python. And then you have the very specific stuff written in C++ or whatever, right? And the most important thing is that we're always stronger with friends. Okay. Thank you. This is the Git repo. It's also here. Feel free to take it or make a pull request. Help me see the Mojo code. All the stuff is there. Thank you.